And Aristotle wrote out some laws of motion, and the first one that he had was that it is the natural state of objects to come to rest on the surface of Earth. It is the natural state of objects, to come to rest on the surface of Earth. Come to rest on the surface of Earth. All right, wind yourself back 2,000 years. What do you think? This is before medieval times. This is before Christ. Yeah. Well, yeah, definitely Homo sapiens, but like post-pyramids here. Pyramids have been around for like almost a couple thousand years at this point. They're, wow. Thanks, David. Thank you. I didn't want to have to say it. So, thinking back 2,000 years, what do you think? Is this a reasonable statement? Yeah, there you go, Spartacus. All right, yeah, it seems like a pretty reasonable statement because if you think about it, would Aristotle have ever seen an object that didn't come back to Earth? No. There's no object that Aristotle could have observed that he could get up into the air and have stay up in the air. That wasn't a thing. So he believed that all objects came back to Earth. And the other piece here is come to rest. Do you think that Aristotle could have ever observed an object that didn't stop moving after an amount of time? No. Everything he observes comes to rest. Now, his explanation for why it happens isn't exactly great. But he makes this note that, yes, all objects come to rest, and it's just what, by the object's definition of what it is, that's what happens. Now, really, he's observing two forces, and I use that word specifically. He's observing two forces in action. Think you can get what those two forces could be? Friction. And gravity. Now, he doesn't name friction or gravity, but he's really observing them, and this is what he's recognizing exist. Now, we operate under Aristotle's understanding of the laws of motion from the from those late BCs all the way up until the late 1600s. So for probably 1,800 years, we use Aristotle's understanding of how things work in order to explain the world that we live in. So aside from it being a reasonable observation, there was one other thing that made Aristotle's teachings really not go away. Anybody know why? You're right, nobody questioned him, but there was a certain power behind nobody questioning him, or that no one wanted to challenge. The Catholic Church. Aristotle's teachings got adopted by the Catholic Church, and since who was in charge of education throughout that time period? The Church. Since Aristotle was being taught by the Church, and you don't question the Church, Aristotle's teachings stuck around for 1,800 years without question, all the way until Galileo and then Newton finally break away and say, wait a minute, we can do better. So Newton finally comes around in the late 1600s. People have arrived on North America, like Europeans have arrived on North America. Late 1600s, we get Newton. All right, and he changes very dynamically from Aristotle's first law of motion here, in that Newton's first law, and many of you guys pointed it out, was that an object at rest stays at rest, and an object in motion stays in motion, unless acted upon by an outside force. An object at rest stays at rest, and an object in motion stays in motion unless acted upon by an outside force. Okay, now we wind up to the 2000s, and even if you want to say the late 1900s, that's fine. An object in motion stays in motion. Where can we observe that and have it be completely true? Say again? A ball rolling will come to a stop.
A ball thrown in space.
Ball thrown in space, or a planet in space, or a star in space. Because if we talk about in space, we don't have any friction, and we don't have any air resistance. So once an object is set in motion, it will stay in motion permanently. Okay? With the ability to go to space, we can now actually observe that. That's something that we can bring into our reality as an understanding. And an object at rest stays at rest. This first law as a whole is also known as the law of inertia, where inertia is simply an object's tendency to resist a change in motion. Is an object's tendency Yes. Will do. See you, Nick. In motion. I have no idea. Yeah. And because I think that the demo is incredible and I've got to show it to you, it stays in motion unless they're acted upon. Newton's second law is the equation. Many of you guys already told me it's a relationship between force, mass, and acceleration. And Newton wrote it as F equals ma. Okay, there's a few things I'm going to change about this, because as written, that's not very clear and actually isn't well done. First of all, we're going to define this as F net equals ma. And what that means is that the sum of the forces in a single direction are equal to the mass of the object times its acceleration. So force net is the sum of the forces in a single dimension. Sum of forces in a single direction or dimension. Meaning that F net is equal to the sum of the forces in some dimension, which is equal to F1 plus F2 plus F3, etc. Are you guys familiar with this sigma notation? That's something we've seen before? Okay. All right. Look good? There's one other change that we're going to make to Newton's second law, because the way it's written doesn't actually make a whole lot of sense. And that's that, and you're going to want to stay with me on this one. Watch close, because I don't want to lose anybody here. F net over m equals a. How many of you are looking at it and saying, well, that's the same equation? Yeah? So mathematically, it's the same equation. Conceptually, however, it shows us a little bit of something different. The way this is commonly written, force net is equal to mass times acceleration. It makes us get the perception that the mass and the acceleration cause a force. But the independent variables, the things that you can manipulate, are the force and the amount of mass that the object has. The acceleration is a result of the force, not the other way around. So by rearranging the equation to show the net force divided by the mass gives us a result of whatever acceleration we observe, we recognize that the independent variables are actually the force and the mass of the object, not the acceleration. So acceleration is the result of a net force, not the other way around. Not the other way. Okay. All right, and lastly, Newton's third law. What's Newton's third law? For every action, there's an equal and opposite reaction. It becomes a little bit more apparent as to what we're talking about. So for every, and instead of saying action, I'm going to say force. There's an equal and opposite reaction, force. There is an equal and opposite reaction, force. Okay? So if I was in space and I threw that rubber band ball, yes, the rubber band ball would start going forward, as according to Newton's first law, indefinitely until something else acted upon it. But according to his third law, I also would start to float backwards compared to the direction that the ball was thrown. How many of you have seen the movie Gravity with Sandra Bullock and out? Sandra Bullock and what was the guy's name? Yeah. Ocean's 11 main actor. I can't remember. George Clooney, thank you. So in multiple scenes, Sandra Bullock uses a fire extinguisher to propel herself around, because the fire extinguisher puts a force out on the gas, and the gas goes and pushes in one direction. By Newton's third law, for every force there's an equal and opposite reaction force, she is pushed in the opposite direction. So we actually see very good representations of Newton's third and first law in that movie. So while some people may have terrible opinions and not have liked it, it's actually a great movie in terms of physics. Okay, so when we're talking about forces, Newton's second law, third law, first law, regardless of what aspect of them we're looking at, we're trying to use them to describe how objects start and stop moving. So forces are used to describe changes in motion. Forces are used to describe changes in motion. All right, so let's just talk about a simple example here. Hunter's gotten a summer job pushing bricks. Don't ask why. He just took the job because it pays. Okay, so there's my pile of bricks. And I'm going to say it has a mass of 300 kilograms. Okay? So as part of the DICES model, the first step was draw. Drawing is actually incredibly important in understanding forces, such that we've actually taken to naming any drawing of forces what we call a free body diagram. So what we're going to do is we're going to try drawing a free body diagram, which is simply a drawing that identifies any forces acting on an object. So free body diagram. Identifies forces acting on an object. All right, so the pile of bricks is sitting there. What forces exist on the pile of bricks? Gravity. I like that answer. So I'm going to draw an arrow showing the direction that that force acts. And I'm going to label it F, and I'm going to write a subscript G to represent that it's the force of gravity. All right. So I could actually calculate the force of gravity, And the force of gravity is always equal to the object's mass times the acceleration due to gravity. So force gravity is equal to mass times g, where g is negative 9.8 meters per second squared on Earth. Okay. All right, excellent. We've got the force of gravity. We could also call this weight, because your weight is simply the force of gravity acting down on you. Okay? So when I say I'm 2,400 newtons, what I'm doing is I'm stating the force of gravity acting down on me. Okay? Let's see here. Well, are there other forces acting on the bricks?
No, none of them.
If that's the case, then those bricks need to be moving down right now. Yeah. Is that what you were going to say as well? All right, yeah. So the ground's pushing up. There's a force that acts from the ground up. And typically we call that a normal force. So I'm going to draw in a force here, F sub n, which is just a normal force. So normal forces exist between the point of contact between two objects, and they're always perpendicular to the plane of contact between two objects. Exist perpendicularly to the plane of contact between two surfaces. All right. We could then assess those forces, and I did say that Hunter's job here was pushing bricks. So he's going to push the bricks. All right. What other forces could I now assess?
My force of pushing the brick.
Okay.
Are the bricks like I lift, so the bricks should be moving.
Okay.
Let's say I use like 500 kilograms of force.
That wouldn't make any sense because kilograms are mass.
500 joules.
That would be energy.
500 watts.
Say again? Newtons. Newtons are the unit for force. I dropped it a couple of times through here. Watts are power. All right, so I'm going to write in force of Hunter here. All right, would anything be resisting Hunter? Well, simply because they have inertia, yes. But would any forces be acting back? Yeah. This one here? I wrote F sub H for force Hunter. No. But really what we're looking at here, anytime you're drawing a free body diagram, put in labels of some sort so it's clear what force you're talking about. What those subscripts are doesn't matter. What does matter is that you know what they're representing so you can use them further. All right, and any forces that are resisting him? Forces that are resisting him. What do you think? Friction. Okay, is that what you're saying, Maggie? Okay, so friction should be acting backwards here. Force, friction. Okay, so we've identified 4 forces that could be acting on this situation. And we want to know a little bit more about friction because there's actually a couple of different kinds of friction. Anybody remember them from 9th grade physical science?
Isn't there 3?
All right, so I heard static. There's our first one. Static friction exists between two objects that are stationary relative to each other. Exists between objects stationary relative to each other. else? All right, dynamic. Another way we could talk about dynamic friction is kinetic friction. Okay, it's just a different term, but it's the same idea. So kinetic friction. And kinetic friction exists between objects that are moving relative to each other. I should state that for friction to exist, they have to be in contact. All right, I'm going to start with just these two. So if you want to call it a coefficient of grippiness, that's fine. Times the normal force that acts on it. Okay. Coefficients of friction are unitless and always unique for two surfaces. Typically, they're found experimentally, such as the coefficient of friction between a banana and a floor is a very, very low coefficient of friction, as determined experimentally last year by a Japanese university who evidently found that that was an important thing to find. Yeah, they got funding to do that.
What did they do?
They tested experimentally the coefficient of friction between a banana peel and a floor. Yeah, basically.
How likely is it for you to step on a banana?
Likely? Don't know. But if you do step on the banana, you will slip because there's like no friction between them, between it and the floor. All right. Let's see here. I've got 3 minutes. I wanted to take one last look at this piece. So when we talked about Newton's second law, we'd said that the net force, the sum of all the forces acting in a single direction, was equal to ma. So one of the tools we're going to use in a situation like this to determine how the blocks are accelerating, and if Hunter can get them moving and how fast, is force-net equations. And for a situation like this, what we're doing is we're summing the forces in each of the different dimensions that the forces are acting in. So I would write something like force net in the horizontal would be equal to the force of Hunter minus the force of friction. Why did I subtract the force of friction? It's going the other direction. Nope. Would be equal to the mass of the bricks times its acceleration. Likewise, I could also write this out in the vertical direction as equal to the force normal minus the force of gravity equals ma. This could be mass or acceleration horizontal, and this could be acceleration vertical. Yeah. This is describing the forces acting on the bricks in the picture above. And tomorrow we'll actually go through working through some of these with numbers, filling in values, finding accelerations, and finding forces.